Okay, so I will be talking about IllinoisGRMHD today. So I will already apologize in advance. If I do say IGM, it means the same thing. Just that's what we use as a shorthand. But if I do say, I will try to not say it, but if I do say IGM, it means IllinoisGRMHD. Okay, this is upside down again. Okay, there you go. All right, so we are part of the, that's very slow. We are part of the TCAN on binary neutron stars simulation, collaboration. And here I'm highlighting a few of us who have directly contributed to the results that I'm going to show you. Without further ado, here we go. So this is an overview of the top. Very slow for some reason. Okay, this is an overview of the top. So I'm going to just introduce and motivate what it is that we're doing. Then I'm going to give an overview of IllinoisGRMHD. I will talk about the updates that we have done to the code, which include a new conservative primitive infrastructure, support for microphysical finite temperature tabulated medium state, and two new codes that we have developed that exist both in NRPy and they have their own Einstein toolkit versions, which are NRPyEOS and NRPyLeakage. And then I'm going to show some latest results from an upcoming paper that we're about to publish and recap and then talk a little bit about the future. I don't know, it's so slow. I don't know why, it's just very leggy. Okay, so I guess most of us that were at LEGO already saw this slide in some, and I think everyone has seen it in one way or another, but in August 2017, 3 detectors saw something quite spectacular, which is gravitational waves from a binary neutron star system. And 1.7 seconds later, the Fermi gamma ray burst detector observed a gamma ray burst from the exact same event, with giving birth to multi-messenger astronomy, I guess, and just emphasizing how much we need to theoretically model these systems. And so the goal here, the ultimate goal, is to model DNS systems accurately and reliably, and we are going to do so for the most part of it, I guess, by using the Einstein toolkit. And there is a good motivation for doing that, and of course is that the Einstein toolkit has a bunch of infrastructure in place to help us, so it can help us evolve the metric quantities with Lorentz like backball, MLBSSN, and Lean. We have GRMHD evolution using codes like IllinoisGRMHD, GRHydro, and Spritz, and there are many others that I might be forgetting. It provides realistic equation of state support. NRPyEOS is one of them, but the standard one is through EOS Omni. Neutrino physics is also available. We have developed NRPyLeakage, but there is also Zomani Leak and Zomani M1. Okay, and there are also a bunch of things that we don't really want to think about that often. So it provides adaptive mesh refinement and efficient I/O and diagnostics, which is a big plus from the Einstein toolkit. Okay, so the idea is that we must be capable of doing these evolutions accurately and reliably, right? So from a computational point of view, our goal is to do this as efficiently as possible. So for typical separations and masses that we're used to studying, simulating the pulling spiral of a BNS system plus the merger phase plus the post-merger phase takes months. Let's say 1 month or something, but it takes something like that, and that's using high-end supercomputers. Now, we often model something like 100 milliseconds of dynamics, but we're really interested in evolving seconds of the simulation per second. And that means that, we have a few options. Like one option is, let's just keep the code running for, I don't know, years or something, that we'll get there at some point. Or we could just try thinking outside of the box, literally, I guess. And so one of the drawbacks of doing this is the fact that we use Cartesian AMR. So it's both a blessing and a curse, I guess. So in the in-spiral phase, this is what a typical grid structure looks like. So you have these little boxes with resolution delta X, and then you have boxes around them with growing resolution. So 2 delta X, 4 delta X, and 8 delta X in this example. This is just schematic, it's not anything realistic. And this is great for the pre-merger phase. Albeit you may say that it is a little bit inefficient still, but it's great for the pre-merger phase. But once the stars have merged and you have a scenario like this where 2 neutron stars merge, and assuming they're massive enough, they'll form a massive neutron star, which will then collapse to a black hole. Now you have a grid structure, something like this, and an accretion disk around it, like that. And this is problematic in many ways, right? So you have, for example, so assuming that the resolution on the outer box is delta X, so up here, you're going to have a resolution of delta X. But down here, the resolution is effectively square root of 2 of delta X. And that's only looking at one direction. But if you look at the azimuthal direction, there's another factor of square root of 2 there that can be inefficient. And things get worse if the disk straddles refinement boundaries like that, because then you have those constant changes in resolution caused by the corners there. And so, just as a back of the envelope kind of thing, the changes in resolution can amount by a factor of 2 when compared to like spherical grids. Then you have jumps in resolution, which is again are factors of 2 because you change refinement levels, and that can cause furious reflections and things like that. Have sharp AMR corners, which can be wasted. You have ghost zones, and you have coarse grids under the fine grids, which can cause inefficiencies as well. And you have the fact that you have AMR boundaries for the fine grids, which can cause further inefficiency. So I think as Zach mentioned before, when we do a fair comparison, perhaps a little bit of an unfair comparison between grids that were used like by Harm 3D, which is a code that can use like spherical like grids, and we try to match the resolution by using Cartesian AMR, it looks like you need like a factor of 100 more points in the Cartesian grids. But if you reduce the size of the boxes a little bit, I think saying that Cartesian grids can be 15 more times inefficient than spherical like grids for modeling this type of system, I think it's quite fair and quite reasonable. Okay, so what are the ways we can deal with this? Okay, so this is what this is very faint, I'm sorry, but this is what late stages of a simulation with IllinoisGRMHD look like. So this is from an equal mass binary neutron star system. We start with merge, form a black hole at the center of that grid, and an accretion disk around it. This is I'm just showing the floor map of the density. Now, this is a little bit schematic, but this is more or less what the AMR structure looks like in this simulation. You have a large Cartesian box there, and then because the black hole has formed, we actually add 2 extra refinement levels there to better resolve the black hole. And so that basically hits the 2 problems that I showed in the other 2 slides. So basically we have not only the inefficiency of having the outer box, but we also have this black hole straddling multiple refinement levels, sorry, the disk straddling multiple refinement levels. So the question is, can we do better than this? And the answer is yes. There's one possible way that we could do better, which is, why don't we use a grid that looks something like this? Okay, it might seem very convoluted to use a grid like that. It seems very complicated, but it's a simple transformation that will lead from one to the other, and coordinate transformation. And we actually have a code that already supports a grid like that, which is Harm. So the question becomes, why don't we, so we developed this, the Handoff package, which basically was designed to do exactly this, transfer simulation data from IllinoisGRMHD to Harm, with the goal of studying the post-merger phase for a long period of time without losing angular momentum from using like Cartesian AMR, where you have, the grid always obliquely crosses the coordinate line, and so you lose angular momentum and things like that. And so what it looks like in practice is, so here it is actually the actual refinement boxes that I'm showing. So on the left, it's going to be an IllinoisGRMHD result from Cactus. And then what we do is we interpolate this data onto a harm grid that this is the XZ plane, and it looks something like that. And then we just continue the simulation in harm. And what does that look like? I'm afraid to show you because I think it's going to be choppy, but okay, let's see what it looks like.
Try the true technique holding up your lap.
Oh, it looks okay. Right. Yeah, okay, it looks more or less okay. So this is all IllinoisGRMHD and Cactus. We're going to zoom out. It's just a visualization trick. We're not doing anything yet. And then the grids are going to change. We're going to, okay, so at this point, we already interpolated the data to harm, and we're going to continue the simulation in harm. And you see that there are no, okay, yeah, there are no like sudden things happening. It just continues smoothly. And this is the same thing by looking from the XZ plane instead of the XY plane. Okay, and yeah, just keep showing it again that it's going to be smooth. Unfortunately, it's not as smooth, but I promise it's smooth here. Hopefully, we'll be smooth. Oh, did we start recording? Oh, we did. Okay. Yeah, I'll make these movies, but they are available on YouTube, and I'll put links to it so that everyone can see them later. Okay, so I actually forgot to add slides to this, but since this has already been asked, is how can we make sure that everything is happening as we expect? So I'll just come back here so that we have a pretty picture to look at while I'm talking about this. It doesn't come back. Oh, sorry, I came back. It's one too many. Okay, but I can start talking. So the idea is that, so how can we be sure that the handoff is working as expected? And one way to do it is, okay, so there's nothing wrong with doing a, I mean, it's not like Cartesian AMR can't do what that grid can do. It's just that we're going to need a lot more resolution in Cartesian AMR, which is going to require a lot more computational resources to do it. And so one way to get an idea if what we're doing makes sense is we stop the simulation in IllinoisGRMHD, we give the data to harm, and then we start them both. And the idea is that they should agree fairly well, because both codes should be evolving the same thing. Of course, there's an assumption here that I also forgot to mention, is that harm is not designed for dynamical spacetimes. And so there's an assumption that is built in when we do this interpolation, that is that the spacetime is static enough that we can transfer it to harm and no longer evolve it. So at that moment, we just stop evolving. And when we determine the time of the handoff has been somewhat empirical. We have done handoffs at different times and just found one that everything works reasonably well. Okay, so now I can skip this hopefully because I don't want to play it again. Did it skip? Okay, we're gonna go now here. So what can we do with the handoff? What kind of physics can we include? So the results that I showed you are basically the first line of this table. So that was for the gamma law equation of state. It had magnetic fields, but it was, let's say, the simplest possible thing that we could try. IllinoisGRMHD was already ready for that. HARM was already ready for that. But since then, HARM was the first one to be upgraded to support both tabulated microphysical finite temperature equations of state and neutrino physics via leakage scheme. And then what I'm going to talk about today is how we have done the same for IllinoisGRMHD, and the details of how that was done is basically what this talk will cover. So now future handoffs that include all this physics are planned, and we're already on the way on doing some of it. I think currently what happened, yeah, I won't go into the details because I won't show those results, but yeah, go ahead, Steve.
So when you're doing the cactus side, you've got a box in the box. I'm just wondering, CarpetX can do better, potentially better refinements, like they're putting the whole box around your disk. It could be just around the disk, and that sort of thing.
Similar to what your Chambo was showing yesterday.
Yeah, I'm just wondering how much of a difference that makes for this.
I don't know. I guess we would have to test, but yeah, it's just a matter of trying it out. Okay. So now a brief overview of IllinoisGRMHD. I'm very thankful for Jay for describing some of the more complicated algorithms that go into Spritz. A lot of them go into IllinoisGRMHD as well. I'm just going to brush over it. I'm not going to go into that many detail. But IllinoisGRMHD is a rewrite of the original IllinoisGRMHD code, or the GRMHD code from the Illinois group that was done by Zach Etienne. So it agrees with the original code to round off error, but it is faster and more concise, so far fewer lines of code. It's fully open source, and it's part of the Einstein toolkit. And it supports GRMHD for dynamical spacetimes, and many things have been studied, including hypermassive neutron stars and single and binary neutron stars, even white dwarfs and black hole systems, I think, have been studied in the past. So there are a lot of things that have been used, that it has been used for. And the latest improvements include hybrid EOS support, which I think is not yet in the Einstein toolkit version, but is already open source and the NRPy repository, and the new tabulated equation of state and leakage. Okay, so first off, we'll start with NRPyEOS and the motivation behind it. So NRPyEOS provides tabulated equation of state interpolations for the Einstein toolkit. Now, of course, if you use the Einstein toolkit in the past, you know that EOS Omni already exists and already does that. So why did we do NRPyEOS? And the reason for it is often when you use a neutrino, include neutrinos, you're going to need to compute things in the table which are a little bit, I guess, you don't often have to compute them if you're just doing GRMHD with finite temperature, like baryon mass ratios and things like that. And EOS Omni supports that, but unfortunately, the only way to get those is to basically interpolate every other quantity in the table. And so these tables usually have 17 quantities in them. And so to obtain one thing, you're going to have to interpolate all 17 of them. So what we did, and I mean, this is personal taste, but I think that the names of the functions in EOS Omni are not very obvious. And so basically, NRPyEOS was developed to avoid all that. So it has a NRPy interface where you can just go there and basically tell. So this is unusual for what a NRPy tutorial normally shows, but this is the very end of the notebook where you're actually about to generate the C code. And right here, I'm only generating, I can actually point like this. And right here, I'm only generating the functions that my code needs. So I'm going to generate a C function where the temperature is known, and all I'm going to interpolate is the pressure. Or one where I'm going to interpolate the pressure, the specific internal energy, and the derivative of the specific internal energy with respect to time or something like that. And this would generate the C codes for us. And there's always, there are other ones there where the temperature is not known, but it's, so by doing this, we have these specialized functions that are sometimes twice as efficient as the one in EOS Omni. It provides a decent speed up when we do that. So the NRPy version of these functions is already available, and in principle, it's not difficult to get them to work with the Einstein toolkit. But the Einstein toolkit version that we use is not open source yet, but it will be made pretty soon. Okay, and then so we also developed a new conservative primitive infrastructure, which includes adding new routines that were not available in IllinoisGRMHD originally. Motivation for that is in IllinoisGRMHD, we did not evolve, we did not keep track of the primitive variables in previous time steps. That's a problem for most Newton-Raphson routines when you're trying to recover the temperature, because if you do not have good initial guesses for your primitives, they just go bonkers. You cannot recover them accurately and reliably enough throughout the simulation. But luckily there are these, so there are two ways you could go about that. One way would just to keep track of the primitives, and that way we would have guesses. And the other one would be to use routines that are that perform fairly well independent of how good or bad your initial guess for the primitives is. And these are we selected these two routines by Palenzuela et al. And by Newman and Hamlin. They have been thoroughly reviewed in a paper by Siegel in 2018. And in fact, our implementation is based on Siegel's implementation, which is open source. And here is just, I'm showing just results from a simple test that was performed in Siegel's paper, and we are mimicking here, where you start with a known set of primitives, then you compute the conservatives, and then you just use as bad a guess as you can, I guess, to try to recover those primitive variables. And then you show what is the relative errors between the known primitives that you started with and the primitives that the conservative primitive routine speeded out. And that's basically what I'm just plotting there, just the sum of the relative errors. In doing so, we realized that recovering whenever, so there are some regions of parameter space in these tabulated EOS tables that are very degenerate in the sense that if you change the temperature just a little bit, that can lead to massive changes sorry, that's not it. So if you change the temperature a lot, you would not see a big change in energy. However, when you're trying to do the inverse, you're trying to recover the temperature from the energy. That means that there's a very wide range of energies of temperatures that you could recover when you're trying to do that table inversion, and that can be very problematic. So we added an option to recover the temperature using the entropy instead, and for those regions of parameter space, which are usually those regions here, where you have high densities and low temperatures, you see that the routines that use the entropy completely outperform the ones that use the energy. But unfortunately, because we only have an approximate prescription for evolving the entropy, we cannot use those reliably throughout the simulation. We just use them as a backup in case the other one fails. Yeah, and so we adapted that to use the entropy, and we do plan on using reprimand, but for now, because it doesn't support the open version, the open source version of it does not support tabulated equation of state. We have not incorporated it into our code yet. Okay. So now we're going to add neutrino leakage as well. So this means that we started from this the standard GRMHD equations, and then because of the tabulated EOS addition, we're going to have to also evolve the electron fraction, which is the fourth equation there, and because of our backup counterprim routine, we're going to also evolve the entropy, which is the last equation, and then we're going to add these two source terms Q and R. And these are going to account for neutrino emission and cooling of the system, not respectively, the other way around. But yeah. So basically, the Q term will remove energy from the system as neutrinos leak away, while the R term will basically change the electron fraction due to this emission, due to the conversion of leptons into neutrinos. Okay, so NRPyLeakage was developed again using the NRPy infrastructure. So it's NRPy based. There are two flavors of it, NRPyLeakage and NRPyLeakage ET. One of them is just designed to work with NRPy and NRPy codes, and the other, but it is infrastructure agnostic, so you could use it anywhere you want. While the other one is specific to be used with the Einstein toolkit. And it is fully Cartesian AMR capable, and I'll emphasize a little bit more of that later, why that is important. Here's an example of what the documentation looked like. I picked a particularly nice looking equation, I guess, where everything is just algebraic and there's not a lot of funny stuff going on, but this is what we strive for in NRPy, to have a cat version of the equations on top, and then within, within I range, let's say, you can still
same line of sight.
Yeah, the same line of sight you can still see. Yes.
So I wanted to ask that before, but there was no time. Now you have lots of time.
Yeah.
You have NRPyLeakage.
Yes.
But here you're not using it. Is there any particular reason why you wouldn't then use NRPyLeakage to parse the latex?
Not really. I think it was mostly laziness on my end, but it's and also I think that I started developing this when NRPyLeakage was still undergoing some changes. So I didn't cross-validate this with NRPyLeakage,
Quite stable.
but I should, yeah.
So would that then be eventually the goal to avoid having, oh, this is the equation, here's the equations typed again, instead of no.
Yes,
this is the equation, this is the latex source.
Ideally, yes. Yes, ideally, yes. But here I have not done that here, but yes, that's a good question. And that's something that we actually plan to do in the future with whatever we implement, just parse it to NRPyLeakage, and that should give us at least one external validation of what we already implemented, and then just move on without having to do this by hand over and over again. And for those who don't know, NRPyLeakage is a module within NRPy that you can put in LaTeX code in there, and it will generate SymPy expressions for you, which are NRPy compatible. So it will parse the LaTeX and make sure that the indices look all right and everything. It's pretty neat. Okay, so our neutrino leakage scheme is very similar to what Jay mentioned for Sprix, meaning that it is based on the same physics that Zomani-Leak uses in producing when they implement their neutrino leakage scheme, which falls back to the O'Connor and Ott implementation. And that's also the same thing that HARM uses. And of course, because we're transferring data from one code to the other, ideally they would be fully compatible and would have the same physics in both codes. And so here's a very simple example that shows that we're at least on the right track. This doesn't fully validate anything, but it's on the right track. So I performed an evolution with IllinoisGRMHD of a very, very simple system. It's just a constant density gas. And I did the same thing in HARM. This is in flat space, so there's no worry. So there's no dynamics in the space-time. And all I'm showing is how the electron fraction and the temperature evolve for different initial conditions, for different initial values of the electron fraction. That's basically it. And just showing that both codes agree to an excellent, it's imperceptible. And I also did the evolution by just doing a standalone NRPyLeakage, which is outside of the toolkit, just to fully validate all the implementations that we have. So next, I would talk about, hopefully this one plays as well. So where we differ from Zomani-Leak is the fact that, as Jay mentioned, Zomani-Leak uses this ray by ray method to find the opacities. So the opacities basically compute, they provide an estimate of how many interactions a neutrino will have before, for example, it leaves a neutron star. So if you follow it along the path, it will tell you more or less how many interactions it will have. So that's very good when your object is centered at the origin and near the spherical, because then you can do, very, very efficient integration ray by ray and find out what the output is. Now, when you have a binary neutron star system, where you have a star on one side of the grid and a star on the other side of the grid, and you have essentially a spherical grid that's going to do that centered at the origin, it's inefficient. That's not to say that you can't do it. You're just going to have to use a lot of resolution in that spherical grid, and it's going to be very inefficient. So one way to do it is to adopt a more local approach, where instead of just doing this integration along radial lines, you do the integration once on the entire grid, assuming that the neutrinos can only propagate to their neighbor. And then you're going to see the effect of that happening. Then you iterate it again, and then they will propagate to the next neighbor, and so on and so forth. So long as you do this enough times at the beginning of your simulation, you should be able to trace all the of what the neutrinos would do by using this pathless resistance approach. It would always the interpretation for this method is exactly that. The neutrinos would probe, in principle, any direction or all possible directions and just pick the one that provides the least resistance. So basically, this is a simple setup where you have a constant density sphere centered at the origin. And I'm going to show here what the iterative process looks like. So it's very fast, unfortunately. So what happens is, so you see that it's not as smooth as I hope it would be. I promise here it's a little bit smoother. I can show everyone, at least the ones that are in person, that it is a little bit smoother. So what happens is, as in the first iteration, you only go up to the first X right here. And then at the second one, information propagates to this one, and then this one, and so on until you reach the top. And then it freezes a little bit because they are changing, but they're changing almost imperceptibly to us. And finally, it stops at iteration 27 or something, because the change in all points is smaller than a user specified value, which is typically like 10 to the minus 8.
10 minutes.
I'm going to stop that because it's very distracting. So that's pretty good, but that's unigrid. So what happens if you do something like this? So this is, of course, something you would never do when you're actually simulating a system. But what happens if you have a constant density sphere And then you put an AMR center here with 2 refinement levels and another AMR center here with 2 refinement levels. So they're completely straddling the surface of this constant density sphere. How do you do that in Cactus? So basically what we did was we use a multi-grid approach. So we start by doing this iteration at the coarsest refinement level. Once we do that, we prolongate that information to the next finer one, and then we do it again, and then we propagate it inwards, and then after we have reached the finest one and have done the iteration, we restrict it back, which means we copy back the information to the part where the grids overlap with the coarser ones, and then we repeat that until we get convergence. And you can see there at the bottom that we again obtain the analytic solution fairly well, even though we have this very suboptimal setup. So this is a very it's a stress test of our algorithm, and it's still working correctly. Okay, so now we perform a little bit of more standard tests. So we have all of this in place. What happens when we try to evolve a TOV? So this is an example without neutrino leakage. But the idea is that we have everything else enabled. So we have the new quantum primitive infrastructure. We have finite temperature EOS, and we are evolving electron fraction and entropy. So this is a 1.4 solar mass cake. It's unmagnetized for this, for the purpose of this example, but the space-time is fully dynamic. So we're not using the Cowling approximation of this one. So the finite resolution that we use to model the star causes it to oscillate. Right? And what we expect is that these would converge away as we increase the resolution. And so this is basically what I'm showing here. So these 3 curves overlap in general, and I just shifted them like by adding a constant so that they don't overlap, so that it's easier to see them. But the idea is that we tried it with 3 different equations of state, and we get between 2.5 and 3rd order convergence, which is expected because our finite difference scheme is 4th order, but because we have the shock capturing scheme that could reduce that down to even 1st order if necessary, you could never expect to get 4th order. You expect something between, let's say 1 and 4, more likely 2 and 4. And so this is, so on the top, I'm showing like the relative change in central density as a function of time, and at the bottom, just the actual change in central density, normalized by the initial value. Okay, and so the next test is an accretion disk. So notice that I'm still using the Cartesian AMR, even though it's said it's not ideal, but that we still have to make sure that it works within the toolkit. And so this is the results from a Fishbone-Moncrief test. And the left panels, so time increases as you go down. Left panel has no leakage, right panel has leakage. And basically the difference between the two, this is still unmagnetized, so you expect the system to be in equilibrium to stay there. But of course, because we have leakage on the left, it's not going to be in full equilibrium. Space-time is fully dynamical. So the disk structure is reasonably well preserved. And as expected on the right, because we have neutrino cooling, the system is a little bit cooler, but it's very it's qualitative, right? It's not. The qualitative behavior is slightly different, but it's still, it looks very much like the same. And now the big test that we did, so this is, okay, so this is an equal mass binary neutron star system. This is magnetized. The initial magnetization is set such that the ratio between the magnetic pressure and the fluid pressure is something like 4%. If I'm not mistaken. And so that the magnetic fields initially are about 10 to the 15 Gauss. It's about 1.4 solar masses each. We have run the simulation in both Idaho National Labs and Frontera. Initial data was generated by Tamai Gupta using Lorraine. And here's what it looks like. So this does include both finite temperature and neutrino leakage. This is what it looks like. It, unfortunately, it's a little bit choppy. I'm sorry. It looks smooth here.
5 minutes.
It's a lot prettier here. Yeah, so the black hole will form and just continue to keep going. So there I'm actually plotting the horizon of the black hole. And so it's not going to evolve much longer. Yeah, I already stopped. And from this, we can and did extract gravitational waves. Here's what they look like. So we also performed a simulation without leakage, which I'm not showing here. But if you compare the two, you see that during the spiral, the gravitational waves are basically, they are the same. They are completely indistinguishable. But after they merge, there's a massive shock, which causes the system to heat up. And when the system heats up and the density increases because you form the hypermassive neutron star, leakage production, the neutrino production increases significantly. And that will cause slight changes in temperature and density that could, and electron fraction that could result in slight changes of the gravitational wave profile. But they're still reasonably close. Okay. So just a brief recap of the results that I showed. So our goal is to reliably and accurately evolve the remnant black hole for astrophysically relevant or very, very long time scales. And now we have the infrastructure to do that. We have HARM 3D ready to go. We have IllinoisGRMHD ready to go, and the handoff ready to go. And so we're testing it right now with more physics added into it. We have already done it for the simpler case. That's basically what I just said. To accomplish this, both HARM and IllinoisGRMHD has been updated to not only include new physics, but physics that is compatible between the two codes. And what the future holds. And so this is, I guess, the interesting thing. So one thing that we want to do is, make sure that everything works well with CarpetX. That we add GPU support. I guess this is sort of redundant if you think about CarpetX will support it, but still explicitly saying adding GPU support. Then rewriting IllinoisGRMHD in this curvy version, similar to what Giraffe is doing, meaning that IllinoisGRMHD would be compatible with any coordinate system, any curvilinear coordinate system that NRPy supports. So spherical-like, cylindrical-like, and yeah, you name it, coordinates. And then finally, one big leap would be to move all, I guess once we have curved IllinoisGRMHD, it might not be that big a leap, but one big leap would be to move it to black holes at home grids that look like this. I forgot to say thanks to Zach. This was generated by Zach, sorry. So this is a much more complicated grid structure, but the idea is that we have a large spherical grid with non-uniform radial sampling on the outside.
2 minutes.
Okay. In there, you have two smaller spherical grids with non-uniform radial sampling. And then inside those, you have Cartesian AMR, but you have Cartesian AMR of non-uniformly sampled Cartesian grids, which might seem very complicated. But Zach will tell you more about it today. And so right now these have been these are being tested for black holes, and then it would just be a matter of plugging in our neutron stars there and see what happens. And of course, another thing that we plan to do soon is to open source all of this that I'm talking about, which will be done hopefully within a couple weeks, and then include the code in the future ET release. Yeah, and just shout out to what some people will be talking about here or have talked about already that might be relevant for these topics in particular.
1 minute.
The first three I would recommend, you already watched Lorenzo's and Eric's talk this morning, but there will be a nice tutorial by Steve this afternoon and by Fede, Lorenzo, and Jay on GPUs, both in NRPy and in the Einstein Toolkit. And then Kirby Giraffe was presented by Terrence, and Zach would talk more about black holes at home today as well. So yeah. So thank you.
Thanks, Leo. So we had a couple questions online. Let's see here. All right, the first one is it possible to implement these non-Cartesian custom grids as a multi-patch system in the Einstein Toolkit, maybe with Llama, for example? If so, why didn't we do it?
I actually have no experience with Llama, so I maybe Zach would be the best one to
So
answer.
on a recent CarpetX call, I called in and offered to help out with a project whereby we would take the Cartesian AMR grids near the strong field and then add spherical grids out in the wave zone, basically pure spherical grids. It was met with at least not a rejection. So, and in fact, encouragement. So I think there's some exciting work there that can be done where black holes at home technology can be imported into the future version of the Einstein toolkit. And I'm excited about that. Second question, typically how much in milliseconds is evolved using IllinoisGRMHD before handoff to harm, say on a 1.4 v1.4 solar mass binary?
So if you include the Inspiro, this would be, I mean, the results that I show you show about, I think, 26 or 27 milliseconds, if I'm not mistaken. But typically what we do before a handoff is we evolve for 1000 M after a black hole has formed. That's the time that we have found, like 1000 M is like, I don't remember, you have to divide by 200 and something, but yeah, milliseconds, but it's not
5-ish milliseconds.
5-ish milliseconds before black hole formation. After black hole formation is what we found to work reasonably well.
Yeah. Any questions in the room? All right, so we are at a short break.
5 minutes.
Oh wait, there's a question from Jay at last second. Which thorn do we use to evolve the space-time? Easy.
Which thorn?
Yeah.
Oh, bicol. Yeah.
We use bicol.
This is the NRPy based version of the PSSN thorn. Yeah.
Okay, great. Well, thanks again, Leo.